Uh, Hi all, welcome back to this NPTEL TA's problem solving session. So we'll be looking at certain concepts today. Not as complex and complicated as the Maxwell's relations that we saw last time. I hope people were able to put things together in terms of looking at the GK sir's lecture and Dr. GK Suresh Kumar's lecture and along with his book. So this time we are going to see about the intermingling of all the forces put together, all the forces or all the fluxes that you have studied about, and yeah, as usual, we'll give some time for people to come into the uh, group, if any. Let's wait for some time. Let's give them 10 minutes. Alright, yeah, it's been almost 10 minutes since the start of the show, so I guess we get started then. So today it's about, as I said, the intermingling of the various quantities that you have been seeing throughout the course. In the book, it has been summarized as such. The various quantities of mass, which is where the driving force is the concentration gradient. I don't want to read the whole thing. Mass, momentum, thermal energy, charge, concentration, velocity, temperature, electrical potential gradient. You should be knowing all these things by now. And now we have a problem or a question. Can diffusion be written as a function of a mass transfer coefficient? So basically, what is the when we say the JA equal to minus DAB into DCA by DX, we what is DAB? DAB is measured, and it's the diffusivity of a given solute in the solution, and it is measured in terms of x squared. I mean, sorry, meter squared per second. And why it is measured in terms of meter squared per second was a question that I had already asked when we discussed this diffusion. It's a very important question. There's a difference between distance and displacement, and the very fact that diffusivity is defined as meters per second and not as meter square per second, sorry, and not as meters per second. It's it it, it, it basically distinguishes distance from displacement. Please go and look at the previous lectures and understand the random walk part of the diffusivity theory. But now my question is a bit different. So basically, if there's a concentration gradient, can it be? So if you think about it, like uh, where you should have come across, mass transfer coefficients in many cases, especially with people dealing with bioreactors and stuff. So can this be written in terms of mass? Can Fick's law can be, or can diffusion be defined in terms of mass transfer? It is a mass transfer, right? It's transfer of mass from position A to position B, where the driving force is the difference in concentration between these two positions, correct? So can it be? Is this an interpret? Can this Fick's law be interpreted in terms of mass transfer? I'll give you a minute to think about it. It's a very easy question, so. In the meantime, let me go check if thank God I checked. Okay, it's still me here. I mean, I'm not surprised. So, well, it's up to you guys. I mean, I put my effort to give you these intuitive insights, and it's up to you to go and listen to the lectures or just mathematically mug up the formulas that needs to mug up whatever that needs to be mugged up to get through this course, get a certificate, and become the domain expert in um, you know transport phenomena, right? So it's up to you guys. Okay, let's go to the So this week we will be looking at the intermingling of, as I said, the intermingling of all the fluxes that we have discussed so far. So the described phenomena in the book is extensive, and as usual, we pick up a very interesting topic within those discussed phenomena, and we will talk about that here. So the thing that I'm going to talk about here is it's a very important concept, transport of charged species across a membrane. So a membrane, when we say a membrane in the context of biology, typically it mostly means a lipid bilayer. Either a naturally formed lipid bilayer or an artificially formed lipid bilayer. So what people do is um, they constitute vesicles which are essentially lipid. They could be monolayers also or bilayers to for drug targeting, etc., and even for studies in basic sciences as to understand the uh, kinetics, say a kinetics of a protein ligand interaction in a membrane, which cannot be studied in vivo. So what they will do is they will reconstitute. It's called in vitro reconstitution of a membrane protein. So they take the membrane protein and then they reconstitute it with an artificially formed lipid bilayer, and they study the protein, either its structure or its interactions or whatnot. So it's very important in the case of biological systems, because the membrane is the cell's skin. It takes care that nothing untoward happens to the sensitive parts of the cell's inner workings, vis-a-vis when we talk about prokaryotes, vis-a-vis we are talking about metabolism, and when we talk about eukaryotes we are talking about compartmentalized metabolism. So it's very simple. So uh, as an aside, if my memory serves me right, around 40% of the proteins are membrane proteins. So membrane proteins have varied roles, starting from signal transduction to uh, cancer resistance. The list goes on. People who are interested should go learn more about it. Now I have two questions. If the above statement is true, that is, if charged species cannot transport across a membrane, why is it so? That is one question. And the second question is, if it is true, and if you think about why it is so, and let's say if it is true, is it impossible for charged species to ever transport across a membrane? These two questions are intermingled, so let's try to answer the first part of the question. If the above statement is true, why is it so? Why is that charged particles cannot enter a membrane, cannot be transported across a membrane? So before that, I think since there may be some people with a non-biological background, when I say lipid bilayer, it means that you should know about detergents, um, which acts to lower the surface tension of the um of the solvent that it is in. But in the context of a lipid bilayer, what we need to understand about a detergent is that it's an amphiphilic molecule. That is, it has a hydrophilic and a hydrophobic part. The molecule can be divided distinctly into a hydrophilic part and a hydrophobic part. So I think you should be knowing about what hydrophilic is. They like water. Hydrophobic means they don't like water. They repel water molecules. So lipids, there are certain lipids, phospholipids, um, many kinds of lipids. I don't want to get into all the types of lipids that make up a lipid bilayer, but there are let's call them lipids for the sake of simplicity. Let's call them lipids. These lipids have a they are amphiphilic molecules. That is, they have a hydrophilic they have a distinct hydrophilic and a hydrophobic segment in their structure. Now what happens is that when these kinds of when these lipids are injected or mixed into solution, the hydrophilic end of the molecule starts interacts with the water, whereas the hydrophobic end of the molecule start to interact with the other hydrophobic ends of the other lipid molecule that come into contact through diffusion. Okay. So what does it have? What does it form? So basically, that there are two lipid molecules. There are two lipid molecules. This is, let's say, the fingernail is the hydrophobic end, and everything else. Sorry, the fingernail is the hydrophilic end, and everything else is hydrophobic. So basically, they will interact like this, right? I mean, sorry, they and the let's say this room is full of water. So the hydrophilic end will both the hydrophilic ends will interact with the water molecules, and the hydrophobic ends, which now includes not only the finger but that extended fist that I'm showing you right now. So this is the hydrophobic interior. So what happens is, now if you think about, uh, a number of molecules across two-dimensional space, basically this happens, and a sheet, think about it like a sheet, or in three dimension think about it like a slab of a hydrophilic moiety, of a hydrophilic part that interacts with water, and a hydrophobic part that interacts with the other hydrophobic part of the membrane. So basically, hydrophilic opposite sides, the whole interior, the whole fist part, and is the hydrophobic uh, area. So I'm repeating again. Now we don't need to say that the fingernail is the hydrophobic end. Let's say this finger is both the fingers are hydrophilic. I mean, let's say that both the fingers are hydrophilic. So we put this into water suddenly, and this part is hydrophobic. Okay, and this part is hydrophobic. These are two lipid molecules we put into water. Suddenly they don't know what to do. They find each other, and then what they do is they start to orient itself like this. And surrounding this whole room is water. There's a hydrophilic end pointing to water, and the hydrophobic interior is just enmeshing with itself. And now think about it in a two-dimensional sheet or a three-dimensional slab. Okay, that's a lipid bilayer. Now tell me, if the above statement is true, why is it so? Why can't charged species cannot transport across a membrane? Or if you think that that's not the case, they can transport, give me an answer. I mean, think of an answer. I'll give you 2 minutes and 1.5 minutes. Yeah. So they can't diffuse easily, right? I mean, see, Now let's say there's a charged molecule on the top of this. Okay, let's say both of the charges are, they are attractive in nature. Okay, now both of these are charged. It can, let's say for best case scenario, it can interact here. Now it needs to traverse this whole enmeshed area of hydrophobic region, which it cannot. It simply cannot, right? I mean, it's very difficult for a charged molecule to do that. So yes, charged molecules cannot be transported across a lipid bilayer. Now the second question: is it unlikely or impossible? 30 seconds. That's all. Not because it's an easy question, because people should know. I mean, 30 seconds. I would say it's next to impossible, because let's take an example. We take ascorbic acid. Experiments have found that the ionized form of ascorbic acid has a pKa of 4. You should be knowing what is pKa. If you don't know, please go refer the site. I mean, refer the web. So at physiological pH, which is at 7, much of the ascorbic acid is in the anionic form. So this anionic form of ascorbic acid doesn't won't it, it typically it takes it's a painful job for it to enter the bilayer. Now what it does is, when it is near, what people have found is that when it is near the bilayer, it takes up a proton. So think about it. It goes against the pKa value. Now don't think about it, in absolute terms. Think about it in statistical terms, that statistical thermodynamics, for a given macro state, micro state. So we are talking about, millions of molecules, 10 to the power 23 molecules, let's say one. Okay, even if, as we say, we are talking about micromolar, we are talking about what, 23 minus 6 is 10 to the power 17 molecules, of ascorbic acid in the solution. So now out of this, the probability that one ascorbic acid molecule which is near the lipid bilayer, which can take up uh, a hydrogen ion, which is a proton, against the pKa rules, the probability is just diminishingly small, right? 1 by 1 10 to the power 17th, it should be in the order of that, the probability. Now what scientists have found out is the way ascorbic acid enters the cell, which is that it takes up a proton, goes into the cell and gives up the proton. Inside it can be ionic, as you all know. So it's next to impossible, if not impossible, for charged species to transport across a membrane. And even if they want to be transported across a membrane, they need help, either in the form of going against, not going against, either in the form of taking up protons. When I say not going against, please refer to my earlier comment on statistical thermodynamics, the statistical mechanics of in this case. So they take up the proton. They need to take up a proton and go inside. So they need help. They cannot get inside so easily. So this is one type of a help. There is another type of a help which is called as, there are certain membrane um, uh, proteins called as transporters, which takes up, which facilitates both the passive and the active transport of these types of charged species. I'm not going to explain it to you what is active and passive means. You should, when you read the text, you'll, or search the web. When you read the text, you will be knowing it. Now, when a charged species, is is there outside, and there are two factors at play here. Now let's take a charged species X plus. Okay, there are two things that are play here. There's a concentration difference in the between the outside and the inside, and a potential difference. Potential difference arises because of the charge of the protein. Sorry, the charge of the ion, and this represents the uh, voltage, the potential difference aspect of this, and that this represents the, we cannot say represents. This is more inclined towards a concentration difference. So what they are saying is, this is the Nernst equation if you look clearly, and when we they assume equilibrium, so there is no net movement of charge across a membrane. We just discussed extensively about it, right? There is no net movement of charge. Now this is the equation for electrodiffusion of charged species. So this is the two factors. I'm repeating again. I'll be briefly. Two factors at play: concentration difference and potential difference. This is the potential difference part. V int and V ext denotes the voltage potentials in the interior or the intracellular and the extracellular parts of the cell, and Cn int and Cnx, Cnx refers to the concentration of the charged species in the intracellular and the intracellular part of the cell and the extracellular environment. Now, given that the intracellular concentration of let's say potassium ion is always higher than that of the outside, so there is a problem in the text that is given, where values, if I'm not wrong, of around 250 millimolar on the inside and 40 molar on the outside, if my memory serves me right. So basically, the driving force, if you think about it, the driving force of potassium is to go from inside to outside, from inside to outside, right? Because the concentration is way higher here. So given that this kind of an intracellular extracellular concentration dynamics exist, how does the equilibrium assumption explain equation 1? So equilibrium assumption, when I say equilibrium assumption, I mean no net movement. There is no net movement of potassium. However, in these kinds of scenarios where there is the concentration of a species is separated by a difference, we have always seen the concentration of the species moves from the point of greater concentration to lower concentration. However, here we are assuming no net movement because of the fact that the space that is separating it is a lipid bilayer. Now what I'm asking you is, what is the consequence of this? What does this equilibrium assumption mean, and how does this explain equation 1 in an intuitive way? So the answer is no, I'll let you think about it. For a couple of minutes. I hope you have understood the question. It's a very simple question. One side the concentration is higher, the other side the concentration is lower. It is separated by a lipid bilayer. The propensity is that the common sense suggests that there should be a net movement of charge from the inside of the cell to the outside, but we know that that does not happen because charged particles don't move. So we have an equilibrium assumption where there is no net movement of ions through the bilayer. Now, given this predicament, how does the equilibrium assumption or no net movement explain, no net movement or no movement, you can take it however you want. Explain this the how does the equilibrium assumption explain equation 1, or I'll give you a hint, the left side of equation 1 in terms of the potential difference. People who have read the text should be knowing by now. People who have not read the text but understood what I said should be able to infer it by now. People who don't have a clue will not have a clue, I guess. Let's wait for a couple of minutes to see where the pieces fall. Even this is a statistical mechanics question, right? How many people understood, how many people inferred, and how many people don't have a clue. Okay, it's very simple, right? So basically, this kind of a concentration difference also sets up a potential difference because these species are charged. So, which means that the potential difference here balances the concentration difference, or the propensity of these potassium ions to just go from the interior intracellular to the extracellular environment is balanced by the potential difference that is set up between the membranes, and which, if I'm not wrong, if my memory serves me right, it should be around, it should be minus 160 millivolts, as given in the example that has been solved in the book. I suggest you go through that. Now that's basically we have understood this part of the electrodiffusion of charged species across a membrane. Now, what kind of uses a membrane potential have? Can you, apart from, we are talking about a potassium ion, biology students, would be knowing that. Um, no, let me ask a question. So, what kind of uses can a membrane potential have? I know most people will get the most common uses, but let's see who gets the one that I think about. You have a minute or two for that, for this. Let's see if somebody has. No, nobody has joined us. Join me. All right. So I know most people would have got that these charged species are used in maintaining the osmolarity of. Just many people might not have got. What many people would have got is that these are the signaling molecules for neural cells and stuff like that. But the in addition to that, there are some uncommon things that you may not know. Like for example, you may not know it. Like for example, these solutes, these charged species, sometimes play the role of an have an osmoregulatory process where they make sure that the osmotic pressure of the cell vis-a-vis the environment is maintained, so that the cell doesn't become flaccid or it doesn't burst, in a hypertonic or a hypotonic situation. Go and find out what, if you're interested, go and understand what I just said. um, Apart from that, apart from regulating osmolarity, it also acts as signaling molecules. Ca2 plus is a known signaling molecule. There are certain species called as reactive oxygen species, which are also known to have some important signaling properties. What else? What I was referring to, as most people may not get it. I don't know whether you got it or not. If you got it, well, you think similar to me. What about the proton motive force, PMF? So, in oxidative phosphorylation, when NADPH is finally being reduced, oxidized, and oxygen is being reduced in the mitochondria, which you should be in mitochondria of eukaryotes, and in the plasma, in the cell, in the cytoplasm of prokaryotes. This oxidative phosphorylation, which includes, I'm not going into the details of the enzymes, which basically where NADH is oxidized and oxygen is reduced, which produces a proton motive force. That is the driving force of life, right? Because this proton motive force that is set up basically is used by a proton pump to generate ATP, which most of you here should know that is the energy currency of the cell. Um, what? So this ATP is like the fuel that we use. It's a petrol of the cell for people who don't have a biological background. ATP is the petrol of the cell. Whenever the cell needs to create manage a uphill process or a thermodynamically unfavorable process, it takes the help of ATP. And certain proteins have something called as a Rossmann fold, which where which has an ATP docking site where ATP gets converted, and the energy of this ATP is will be used by the enzyme to execute such an thermodynamically unfavorable process. So ATP is the energy currency of the cell, or the petrol of the cell. And why is it the petrol of the cell? People who are interested in finding it out, go find out. It has something to do with basic chemistry, resonance. Okay, so figure it out. Who are people who are interested, or people who just want to understand the mechanics of it and become domain experts, be my guest. So yeah, we are going to continue here. Now we looked at the transport of charged species, of one type of charged species in the case in the previous example. Now what if there are many charged species? Consider different charges moving independently of each other. Problem: does membrane potential have to remain the same? What will happen if it increases, decreases, or fluctuates rapidly? Try and visualize the bilayer environment. But before we go into this problem, I would like you to look at this called as a Donan equilibrium. So what happens is that, as I said, that a cell has a constant, not a constant, a typical membrane potential. It could be any number. For example, in the example given in the book, it was around it was minus 160 millivolts. So for a single species or for a multiple species, it doesn't matter. If the cell needs to maintain a certain amount of potential, the flow or the flux of these ionic charges will be such that the the cell potential difference is maintained. So if the cell potential difference is such that per unit of time only 3 units of monocharge species can go inside of a cell, and we are and there are there are multiple charge species outside, only 3 will go in per unit for that unit of time. So that is an intuitive explanation of the Donan equilibrium. If you read the text and listen to the lectures, you will understand it much better. Now let's go back to this question: does membrane potential have to remain the same, or leave that part out? What will happen if membrane potential increases, decreases, or fluctuates rapidly? Try and visualize the bilayer environment. I'll give you a minute for it. What will happen if the membrane potential, so all these ions, they tend to accumulate near the membranes, especially on the intracellular side. So what will happen if the membrane potential increases, or if it decreases, or if it fluctuates rapidly? The answer is simple, right? Basically, the Doran equilibrium will keep changing. The Doran equilibrium will adjust to the new potential environment. And if it fluctuates rapidly, the equilibrium won't be equilibrium. Correct? It's a simple answer. Um, but I'm sure homeos, homeostasis is important. When you say you should know, if for people who don't know what homeostasis means, is basically the maintenance of certain conditions. And I'm sure membrane potential is one such condition where homeostasis is important for the cell to function well. All right. So since we have looked at a portion of the portion of the book which goes into which is nostalgic in nature, or in other words, it delves into whatever we have seen before, and it packs it into in one unit where multiple types of fluxes interact with each other. I wanted to go back and give you some nostalgia of my own. Remember in the first class I started about discussing the basic tenets of calculus. So I just wanted to give you a problem. Let's say that I need to travel a distance x. Let's say 1 kilometer, 10 kilometer, whatnot. Be my guest. Let's say I need to travel a distance x. I do it within a finite time frame. Okay. Let's say I need to travel from Chennai to, not Chennai, from my home to the institute. I do it in 10 minutes typically, so it's a finite time frame, right? We agree on that. Good. However, during my travel, I wondered that on reaching half the distance, let's say the distance between my home and the insti is around 5 kilometers. Let's say at 2.5 kilometers, I just have a flash. I just stand there and think, now if I cut up the rest of the space that I need to travel, so the rest of the space is the remaining x by 2, right, which is in this case 2.5 kilometers. If I cut up the remaining 2.5 kilometers into halves, let's say 2.5 kilometers can be given as 2.5 kilometers by 2. Sorry, it's okay. Yeah, 2.5 kilometers by 2, or in this case, since 2.5 kilometers represents x by 2, here I am giving it as x by 4, x by 8, x by 16, x by 32, etc., etc., and so on and so forth. I would end up with an infinite amount of space, right? So I can see x by 16, x by 32, x by 64, x by 128, x by 256. I can keep on going. X by 1024, because there is no end to numbers are infinite, right? So this 5 kilometers, which I know is finite, have somehow by doing this mathematical um, jazz, I had converted a finite space into an infinite space. So I did not do this. A Greek philosopher in the good old times of the Greek civilization called Zeno did it, and this is one of his paradoxes. There are many paradoxes. People who are interested, if you are interested in this, there are many paradoxes that have been constructed by mathematical paradoxes constructed by Zeno. That if people are interested, they can go look at it. But coming to this, how will I solve this? I mean, I have just converted a finite distance into an infinite distance. And coming to the second point is that this implies that I've traveled infinite space in a finite time. So I'm Flash, right? I'm the superhero Flash. I just run so fast that I can reach infinity, you know, and beyond. Oh, perhaps I'm Flash Lightyear. So where I'm wrong here? So if I'm wrong, I'm wrong. And if so, how? So my question is very simple. There is something wrong in dissecting a finite space into infinite space. However rational the first point may seem to be, there is a problem inherent. It's not a problem. there is a solution for it, which makes that uh, which solves Zeno's paradox. So I gave you a clue. I wanted to go and become nostalgic and talk about calculus, and yeah, this has something to do with calculus. So there are 5 more minutes remaining. I'll give you 2 or 3 minutes to think about it, and then I'll give you the answer, and then we'll end the class. Anyone home? I guess not. I'm getting some increased views in the YouTube channel, which is encouraging. Just moved some videos have moved to double digits. Happy, but some people are saying it. Good. Yeah, I'll just let you be with the Zeno's paradox while I wonder about what went through the mind of that Greek philosopher, which made him construct such a beautiful piece of art, paradoxical piece of art. Alright, so the answer is simple. As I keep dividing the space into halves, the negligibility in the number of that space increases, or as I increase it, x tends to 0, limit x tends to 0. So basically, finally, calculus was able to explain Zeno's paradox, and Wolfram Math World, the website, has a very if you read the first block, first paragraph of that page, you would they have elegantly, without using a lot of mathematics, they have elegantly and explained this part of Zeno's paradox. So people who are interested, go look at it. So that's about that, people. I hope you enjoyed today's lecture, and let us meet next week. All right. Okay then. See you. Bye bye.